Hello everyone, welcome to Physics Unwrapped YouTube channel. In this channel, you will get concepts related to physics as well as PYQ of various examination. In this video, I am going to explain about nuclear shell model. Okay, before going to nuclear shell model, we shall study about magic numbers. What is this magic numbers? Magic numbers are nothing but these are proton and neutron numbers, but they have different properties when compared to other protons and neutron numbers. We have magic numbers like this: 2, 8, 20, 28, 50, 82, and 126. Proton or the neutron numbers are considered as the magic numbers. Okay, let us know what are the properties of these magic numbers. What are the properties? The properties are it has high stability and binding energy per nucleon is very high and neutron capturing power is very less. Okay, let us go move to the next slide. In the next slide, in this slide, we are going to study about energy levels or the shells under nuclear shell model. This is what I am written here represents the energy levels on the shells. Here, listen carefully. The half and the 3 by 2 and the 5 by 2, 1 by 2, 3 by 2, what you are observing, these are called as a J, where j can tag the values 1 by 2, 3 by 2, 5 by 2, 7 by 2, so on. What is this j? J is nothing but total angular momentum. It is called as total angular momentum, or you can call it as a spin, that we have already studied in our previous classes. And can you see here s P, D, F? What are these SPDF? SPDF are nothing but the subshells. And here can you observe 1, 1, and here 1, again here 2 and 3, 1, 1, 2, 2, and these are nothing but N. It is a principal quantum number. Yes. So completely this is called as we represented by a term symbol. The term symbol is written as N and L to the subscript J, and to the superscript it is 2s plus 1. Okay. So this is the term symbol, and term symbol representation is this, and this completely which I have written in the red mark is nothing but energy levels or shells. I am not going to deep into this nuclear shell model. What is required from the exam point of view, that only I am explaining in this video. The questions they will ask in this, especially in this topic, is to find the spin parity of an atom. Okay, to find what is the spin and what is the parity of an atom, we have a general formula. That general formula is to find the parity. The parity is found or like this. The mathematical formula I have already written here. It is minus 1 to the power of L. Previously I have told you that L is a orbital angular momentum and the spin is J. We have three set of rules to find the spin or the J. It when the proton or the neutron number is odd, even, or even odd, what will be our spin and what will be our parity. With the example we will find out, then it will be clear to you. Okay, we shall find what is the proton number. The example I took is boron 511. 5 is the proton number and 11 is the atomic mass. Okay, so the proton number is here 5 and the neutron number I want. What are the magic numbers? The magic numbers are nothing but the proton and the neutron number, right? And what is this nuclear shell model? It is playing with these magic numbers. So I want this neutron number. Neutron number is nothing but mass number minus proton number or the number of electrons and the number of protons, we will get the neutron number. So it is 11 minus 5, it is nothing but 6. Now concentrate here, we need to take the odd number, that is proton, and write its energy levels. So it is 1s of 1p 3 by 2 and 1p 1 by 2. This is how it was there in the second slide, right? This is the electronic energy levels or the shells of a nuclear shell model. So what we have, 1 s half and 1p 3 by 2 and 1p 1 by 2. This is sufficient for this atom. So we have here j to be half, and I need to fill 5 proton numbers. So S can accommodate maximum proton numbers to be 2. So P can accommodate maximum proton numbers to be 4. Here if it is a 3 means add 1, that is a trick, it will be P to the power 4. Here we have a 1 means add plus 1, it will be 2. So how much I need to add, it is 5. So already I accommodated 2, then how much is left? 3. So P can have 3. This is not required by you. So here this is the unpaired proton, right? That we need to concentrate. The unpaired proton only we need to concentrate. So here J is what? 3 by 2. It is our spin. And how we need to calculate the parity? We need to calculate the parity, that I'll be telling while taking the example. So this is my spin. Everyone got? I hope that everyone got. We will be moving to the next slide. Yes, this is the case when it is odd. Okay, if it is a odd case, what will be our parity? How we need to find the parity? So the parity is here minus 1 to the power of lp plus ln. It is a orbital angular momentum of a proton plus orbital angular momentum of a neutron. Sometimes I use it as a small n, and sometimes I'll be using a capital N. It is one and the same. Here it represents the neutron number only. So to find the spin, the j vector, it is nothing but the spin or the or the angular momentum or the total angular momentum we call, that is nothing but j subscript p vector. This is a angular momentum of a proton plus angular momentum of a neutron. How we need to find means, with the example I'll clarify you. Take the example of a nitrogen. The nitrogen atom has same number of proton as well as same number of neutrons, right? That is odd numbers we will be getting. Like see, proton number is here 7 and the neutron number is also here 14 minus 7 is 7. First, do the energy levels for this any one of this. So I'll do for both. It is 1 s half to the power of 2, 1 s 1p 3 by 2 to the power of 4. How much is left? 1 is left. So it will be 1p 1 by 2 to the power of 1. So here jp, which is equal to half, and lp, which is equal to how much here? Lp, which is equal to how much here? I'll tell how to find this. Okay. Next, do for the neutron number also. It is 1 s half to the power of 2, the same thing, 1p 3 by 2 to the power of 4, 1p half to the power of 1, right? So here j n, which is equal to half. Again, what is this? ln. So I'll be telling here how to find the L, that is orbital angular momentum. Okay, if we have a s suborbital means the L value will be 0. Okay, if we have a subshell p means our L value will be 1. If we have a subshell D means our L value will be 2. If we have a subshell F means our L value will be 3. like that, so on it will be going. What is the orbital angular momentum, like how we need to calculate, you got one idea, no? So here what is the subshell we have here p, right? For p, what is the value for l? It is 1, right? So here write it as 1, here also it is 1. I hope everyone got it, is clear, right? Next we have, I'll write down the values here for the calculation purpose. We have jp which is equal to half, and jn which is equal to half, and lp which is equal to 1, and ln which is equal to 1, right? On adding all this, that is jp according to the rule, jn plus lp plus ln, that is equal to half plus half plus 1 plus 1. How much we get? 1 plus 1 is 2. Half plus half is 1. 1 plus 2 is 3. So, how much we got? 3. 3 is again the odd number, right? Again the odd number. Go to the rule. If it is again the odd, then J, that is spin, which is equal to Jp plus Jn. That is the total momentum of a proton plus total momentum of the neutron, right? So here it will be J, which is equal to Jp plus Jn, that is half plus half, that is equal to 1, right? So 1 is my the value for J. Everyone got? Yes, I hope everyone got. Shall we move? Yes. How we need to find the parity? The parity here is minus 1 to the power of Lp plus Ln. This is the formula, right? Yes. We shall see what will be the parity for nitrogen atom. It is parity which is equal to minus 1 to the power of Ln plus Lp. So it is minus 1 to the power of what is Ln Lp? It is 1 plus 1. How much we got? 1 plus 1, it is 2, minus 1 to the power of 2 minus 1 to the power of even number is plus 1. So what is the parity we got? The parity is 1 here. Okay, it is clear? Yes. Next we will be moving to the third rule called even. If it is a even, both proton and the neutron number is even means, then our J, that is a total angular momentum, will be 0 and the parity is always positive. Yes, the concept, I hope the concept is clear for everyone. We shall move to the problems which was asked in KSET paper. Okay, first we shall solve the first question which was asked in KSET 2018. According to the shell model, the ground state spin parity of boron 511. This is the same example I took for explaining the spin parity, or the spin I can call. So it is, we shall do for it. It is boron 511. So number of protons, how much we have? 5, and the number of neutron number is 11 minus 5 is 6. So take the odd value and write the energy levels. It is 1 is half, 1 p 3 by 2, and 1 p 1 by 2. So how much the S can accommodate, S shell can accommodate? It is 2 protons, and the p, how much it can accommodate? 4, but how much it is we want? It is only 3. So this is the unpaired proton, right? We are interested in only the unpaired proton. So take down the J value according to the term symbol. The subscript is J, so J, which is equal to 3 by 2. And here we have a P. The subshell is our P, so P means that is L, which is equal to 1, right? According to the rule, if it is S, it is 0. If it is L, if it is P means it is 1. Okay, yes. So the parity formula is, parity is capital P and the subshell is P. I am using here small p. Okay, this is the parity symbol. Parity which is equal to minus 1 to the power of L. It is minus 1 to the power of 1, which is equal to minus 1. So I have my j, that is spin, which is equal to 3 by 2, and my parity, which is equal to 1 minus 1. So completely we can write it as 3 by 2 to the power of minus 1, or minus you can say. So our option B is right. Can we tick on that option? Yes. So it is very easy to solve when we know the concept clearly. Yes, we shall move to the next question, which was asked in KSET 2016. Yes, we need to find the ground state spin of lithium 7. They have only mentioned here the neutron number, not the proton number. As we know, the lithium is 3 in the periodic table, right? It is having a 3 atomic number, right? So our proton number will be 3 and neutron number is 7 minus 3 will be 4. We are interested in a odd, so it is 1s 1 by 2 and 1p 3 by 2. How much it can accommodate in the s subshell? It is 2. In the p it can accommodate maximum 4, but it is our requirement is only 1, so we'll place 1 here. So we are interested in an unpaired proton number, so it will be j, again j, which is equal to 3 by 2. What they have asked this time, they have asked only the spin. So our spin is 3 by 2. Option C is the right answer. Yes. Yes, we shall move to the next slide. In the next slide, what we have, the first question is the magic numbers are. It was asked in the 2016 KSET examination. The magic numbers are. Go to the first slide. I in the beginning of the concept only I have explained about the magic numbers, right? What are the magic numbers here? These are nothing but the proton and the neutron numbers. It is 2, 8, 20, 28, 50, 82, and 126. Yes, we shall move to the question now. What what are the options? Look clearly, and we are very clear. The first option is right, right? Yes. Even they have left the one magic number. The complete magic number is 2, 8, 20, 28, 50, 82, and 126. So this we can see, leaving 28 we can see in the first option, right? So the first option is correct, and this was a very easy question. Yes, we shall move to the next question. According to Shell model, the ground state spin parity of oxygen. We know the oxygen atomic number is, and this was asked in 2015 KSET examination. We know that the oxygen number is 8, atomic number, right? It is oxygen 850. So number of proton number is 8 and the neutron number is 15 minus 8, it will be 7. We are interested in always the odd numbers, so it will be 1 s 1 by 2, 1 p 3 by 2, and 1p 1 by 2. This much is sufficient, I feel. Here it can accommodate 2, here it can accommodate 4, here it can accommodate how many? 2. But how much we require? Only 1 we require, right? Yes. So from here it is clear the j, that is spin, which is equal to half. And how to find the parity? Parity is minus 1 to the power of L. I told you for P, that is P subshell, the L value which is equal to 1. So it will be minus 1 to the power of 1, which is equal to minus 1 again. We got the parity to be minus 1 and we got the angular momentum or the spin to be half. So it will be the spin and parity will be half to the power of minus 1 for the oxygen. So our option C is right. So right answer is option C, that is half to the power of minus 1. Thank you everyone.